Okay, I just completed the entire lab and realized I wasn't filming. I pressed the button and it wasn't filming. So we're gonna go through this again. This is actually the third time that this has happened, so hopefully the third time will be a charm. So we got our fulcrum was at 46.0 centimeters. So this is where the fulcrum is over here, 46. Here's my one weight over here, and here's my other weight over here. Now, this weight was over at 1 centimeter, and this weight was over at 90 centimeters on the other side. So the actual teeter-totter is not 100 centimeters. The teeter-totter is actually between 1 and 90. So the actual teeter-totter is going to be 89 centimeters. So the length of this will be 89 centimeters total. Question is, what is this R1 over here? Here's this. So the difference between 46 and 1 will give me 45.0. Here's my R2 over here. And these are equal masses. And if I take 90 minus 46, I will get 44. So I realized that I should actually, these numbers should be the same. However, this is a little setup, and we're physically maneuvering this, so it's not going to be exact. So let's convert these into meters. So this is going to be 0.46 meters. This will be 0.45 meters, and this will be 0.44 meters. So that's the first scenario, and now what we're going to do is we're going to be adding a second weight to the second mass to make it 1.0 kilograms. So I am doing this right now, and then I'm going to be moving the fulcrum, and I'll show you what the end outcome will look like. So these masses have little hooks on the bottom that enable them to hook to each other. So now I have two masses, but I feel that my two masses is very, very heavy. So what I need to do is I need to now move my fulcrum to make this nice and balanced. So I'm going to show you what this looks like now, very carefully. So it's almost balanced. Here my hand's taken off of it, and I'm now at 60, and right about 60 is the balancing point. So I have my two masses over there, and I have my one mass right there, and it's not touching the table. I'm not tricking you guys. So the balancing point for that is going to be at 60. Okay, so let's go ahead and we'll record this. I'm going to take this and move it onto the table just so that nothing falls again. So here's the second scenario. My fulcrum is now at 60. So what's my distance between 60 and 1, where the other weight was? It is 59.0. Actually, the fulcrum is 60, sorry. Fulcrum is 60.0. The distance between 60 and 1 will be 59.0. Distance between 60 and 90 will be 30.0. Let's convert these into meters, 0.60, 0.59, and 0.30. Again, these are all now in meters. That's the second scenario. Now I'm going to do this a third time by adding another weight over here on this side on the 90. So of course that's going to add more weight to this side, and again I'm going to have to move my fulcrum over even more towards where the weight is. almost balanced. And then I'll show you what this looks like. Okay, so I have now, there's my setup. That's my stand for my iPad while I do these. So I have my 3 weights over on the other side, and you can see my 1 weight over there, and it's fairly balanced at 67. I could take it over just a teeny tiny more, but then it's going the other way. So 67 seems to be a really good balancing point, and that's the number that we will go ahead and use. I'm going to take these off. Okay, so now for this trial, we had 67. So my fulcrum's at 67.0. The difference between 67 and 1, my R1 is going to be 66.0. Difference between 90 and 67 will give me 23.0. And we'll now convert these to meters and 0.23 meters. So this is finding the fulcrum physically, but on the homework and on the test, you'll need to find it mathematically. Okay, so the first one is going to be easy, and I messed up the pages. This will be coming later, so you guys can go ahead and just keep that in your lab packet. We're going to be working on this page for the calculations. So first, use the formula for net torque to calculate R1. Note when substituting for R2, the total length is the difference between the 2 positions, not the length of the ruler. So second, since R1 plus R2 equals the total, we're going to determine R2. So if you remember, the total is going to be 0.89 meters because the weights are at 1 centimeter and 90 centimeters. So the total length is actually 0.89 meters. If we're solving for R2, because if you remember the formula for net torque is equal to torque 1 equals the torque 2. Now torque is equal to the force times the radius times the sine of theta, but if you remember, these are at 90-degree angles, and the sine of 90 will be 1. So for the teeter-totter example, it's just going to be the weight times the radius equals the weight times the radius. Since for the first one we have equal weights, we would expect the radii to be equal, and ours was fairly close. It was 45 and 44, so that's fairly close for that. And we now have to calculate what is the weight going to be for each of these scenarios. So remember, weight is equal to the mass times g, and g is 9.8. So we'll convert these from 0.5 kilograms, and we'll get them into newtons. So let's go ahead and do that first. So let's do a couple calculations. If I have 0.5 mass times 9.8 meters per second squared, this will give me 4.9 newtons. So this will be 4.9 newtons, this will be 4.9 newtons. Okay, this again will be 4.9 newtons, and this is going to be double that because it's double the mass, so this will be 9.8 newtons. This again will be 4.9 newtons, and this will be 3 times this in newtons. That will give me 14.7 newtons. Now that we have that, we have the weight, and we have the radii that we're going to try to calculate. So if I'm trying to solve this, let's plug in the formula for net torque. So remember, tau 1 is equal to tau 2. So I have Fg1 times R1 equals Fg2 times R2. Now I have each of my weights, and I know that these add to 0.89, and I want to solve for R2 by subtracting an R1 from both sides. So my R2, if I subtract an R1 from both sides, will equal 0.89 meters minus R1. And I'm then going to plug that into this over here. So I have my first mass, my mass 1, is going to be 4.9 newtons times R1 equals 4.9 newtons times R2, and again R2 is equal to 0.89 meters minus R1. I could then divide 4.9 newtons from both sides, and those will cancel, those will cancel. I'll be left with R1 is equal to 0.89 meters minus R1. I can add an R1 to both sides to cancel those, and I will get 2 R1s equals 0.89 meters. If I divide both sides by 2, R1 will then equal 0.89 divided by 2 will give me 0.445 meters. So now I don't need to do all the same thing for R2 because I have the formula up here. R2 equals 0.89 meters minus R1, but we've already solved for R1. So this will be 0.89 meters minus 0.445 meters, and this will give me 0.445 meters. So my R1 and my R2 mathematically should be the same because they are the same mass. So where's the fulcrum going to be? If these are my radii, so this is how to find the fulcrum. Well, remember the weight was at my 1 centimeter, and if my radius of 1 is 0.445 meters, if I convert the 1 centimeter to 0.01 meters, I have 0.01 centimeters plus the radius, that will find the fulcrum, 0.445 meters and meters. This will give me 0.455 meters. So my fulcrum mathematically